Video number 39 plus, the treasures of dimensional analysis. Hello everyone. Today's video naturally follows the previous one on scale effects and will be followed by a video about orders of magnitude and the sense of reality. Why is dimensional analysis so powerful for guessing formulas or correcting mistakes? It is because the simplest physical laws are multiplicative. In the sequel, for the sake of simplicity, I shall only consider the subdomain of mechanics. For more general considerations, you may consider the links given in the comments. Point 1. The MLT system. In pure mechanics, everything is expressed on the basis of mass, capital M, length, capital L, and time, capital T. This is called the MLT system. Any usual mechanical quantity is expressed using these three fundamental quantities, measured respectively, for complex historical reasons that we shall not recall, in kilogram, meter, and second, the first three units of the international system. Point 2. Scientific formulas and dimensions. The fundamental idea of dimensional analysis is the homogeneity of formulas. By this we mean that the two sides of an equation must be of the same nature. A mechanical quantity, capital A, is associated with the dimensional equation dimension of capital A equal m power A, L power B, T power C, where the exponents A, B, C are positive, zero, or negative numbers. If in a formula we have k m power A, L power B, T power C equal k prime, m power A prime, L power B prime, T power C prime, with k and k prime dimensionless constant, for example 1, 25, or pi, it is necessary that A equal A prime, B equal B prime, and C equal C prime. All physicists know by heart the dimensional equations of the usual physical quantities. For example, velocity, the distance traveled per unit of time, has dimensions L over T or Lt minus 1, corresponding to A equal 0, B equal 1, C equal minus 1. An acceleration, velocity of the velocity, has dimensionality Lt minus 2. A force, mLt minus 2, and energy, mL2t minus 2, the product of a force by a length. They use this knowledge to balance equations, detect calculation errors in student papers without having to check the details, and possibly correct their own errors when their calculations lead to bizarre conclusions, because everyone can make mistakes. Point 3. Some classical formulas from the viewpoint of dimensional analysis. Newton's second law, F equal ma. The second member, ma, has dimensions mLt minus 2. So it is indeed a force. Actually, it is by this formula that we define the forces and the unit of force, the Newton. Einstein's formula E equal mc square. C square is the square of the speed of light. The product of the square of speed by a mass has the dimension of an energy. Besides, the kinetic energy of a mobile of mass small m and speed small v is half of mv square, which resembles Einstein's formula up to the factor of 1/2. Potential energy of gravity. To raise the mass small m to the 8th small h, it is necessary to expend an energy capital E equal gmh, where proportionality to both small m and small h, therefore to their product, is obvious by an elementary argument. Since the dimension of E equal mL2t minus 2, and dimension of mh equal ml, we find by division that g must have the dimension L t minus 2 of an acceleration. This is precisely what is called the gravitational acceleration. Point 4. Some classical successes of dimensional analysis. This method is very powerful for guessing formulas when we know which quantities are involved in a phenomenon. For example, Galileo had noticed that the period of the small oscillation of a simple pendulum depends only on its length small l. As we imagine that the value of the acceleration of gravity small g also plays a role, we are led to suppose capital T, the period, equal k L to the power x, g to the power y, with k universal dimensionless constant and x, y are unknown numbers. But as the dimensional analysis of capital T corresponds to the value 0, 0, 1 of the exponents, from dimension of T equal L power x, L power y, T power minus 2y, we deduce that x plus y equals 0 and minus 2y equal 1, hence x equal 1/2 and y equal minus 1/2. Finally, capital T equal k square root of L over g. The differential calculus, discovered well after Galileo, confirms this with k equal to pi. If we knew small g, and we knew it roughly for other reasons by observing the fall of bodies, we could have guessed the constant 2 pi by doing experiments. And after all, today, this kind of situation could happen again. Even the Pythagorean theorem can be found as a consequence of dimensional analysis, which implies that a similarity of ratio k on a plane figure has the effect of multiplying its surface by k squared. For two right triangles having an equal angle other than the right angle, it follows that the ratio of the areas is equal to the ratio of the squares of the length of their hypotenuses. This is the basis of a proof of the Pythagorean theorem found by Einstein as a teenager. This proof was also mentioned in a work by the mathematician Adrien-Marie Legendre. Point 5. A more elaborate example. The gravitational pressure at the center of a star. A pressure is, by definition, a surface density of a force divided by a surface. The pressure at the center of a spherical star, associated with the mutual attraction between the atoms, involves the total mass M and the radius R of the sphere. Let us see what comes out of a more precise calculation. It can be assumed that the basic distribution is spherically symmetric. In this case, the total mass M of small r contained in the ball with center 0 and radius r is given by the formula m of r equal integral from 0 to r of 4 pi s squared rho of s ds, where rho of r is the volumetric density at any point of the sphere with center 0 and radius r. We have, of course, capital M equal m of capital R. The fundamental theorem of hydrostatics gives that the gradient of the pressure capital P of R, evaluated in newtons per square meter in the system of MKS unit, with respect to the radius R, is negative and given by the formula P prime of R equal minus rho of R g of R, where g of R is the acceleration of gravity at the distance r from the center O. Note first that this formula is quite homogeneous. Dimension of P' of R equal m L t minus 2, L minus 2, L minus 1, equal ml minus 2 t minus 2, while dimension of rho of r equal ml minus 3 and dimension of g of r equal lt minus 2. Therefore, dimension of rho of r g of r equal dimension of rho of r dimension g of r equal ml2 t minus 2. On the other hand, we know, and this is a classical result due to Newton, that g of r equal capital G m of r divided by r squared, where capital G is a constant of universal gravitation. Assuming the surface pressure is negligible, we therefore find capital P equal capital P of 0 equal integral from 0 to capital of R of capital G rho of R capital M of R divided by R squared dr. For example, if rho is constant, this gives capital M of small r equal 4 pi over 3 rho r cube. Hence, capital P equal 4 pi over 3 integral from 0 to r of capital G rho square r dr equal 2 pi g over 3 rho square r square equal 2 pi g over 3 over 4 pi square m over r square square. Hence, capital P equal 3 over 8 pi capital G m square over R4. This formula is homogeneous because capital G m square over R square is the force of attraction of two masses equal to m separated by a distance r. Therefore, capital G m square over R4, a force divided by a surface, has precisely the dimension of a pressure. In fact, rho of r obviously depends on r, and under the effect of gravity, it is logical to think that it is a decreasing function of r with a possible infinite maximum at the center. In this case, we have capital M of r greater than or equal to the integral from 0 to r of 4 pi s square rho of r ds equal 4 pi over 3 r cube rho of r. This implies that m of r over r cube is decreasing, and we deduce quite simply that capital P greater than 1 over 4 pi capital G m square over R4. A lower bound, slightly lower than the value obtained for a constant rho. We recall that the unit of pressure is 1 Pascal equal 1 Newton per square meter. Sometimes one uses 1 bar equal 10 to the power 5 Pascal. 1 bar is close to the atmospheric pressure at 0 degrees centigrade at the level of the sea. With the last inequality, one easily finds that the pressure capital P at the center of the Earth exceeds 10 to the power 11 Pascal. By another method related to seismology, we find rather 4 times 10 to the power 11 Pascal equal 4 million bars. Just remember that capital P is about 4 million atmospheres. The same calculation for the Sun gives only P greater than 3 10 to the power 12 Pascal. It is strangely a bit low if we compare with the Earth, but the currently accepted value, reflecting a considerable increase in the density as a function of depth, is almost 10,000 times greater, 2.5 10 to the power 16 Pascal, or 250 billion atmospheres. I conclude by wishing you the best possible new year with a lot of new discoveries. Every day's learning is the secret of a healthy life.